everyone. So welcome to the Trig Workshop. We're going to go ahead and get started with section 7.1. So on your first problem there are 4 visuals, and I want you just to think for a few seconds, what do those visuals have in common? So the thing that they all have in common is that they all represent circular motion, and that's really what trig is about, is representing circular motion. So in our worksheet here, we're going to think about looking at a bicycle tire, because obviously that is a circular object, and we're going to think about a white dot on this tire, and we're going to think about how that dot is moving around the tire. Okay, so go ahead and just take a second and read through those first kind of like 3 paragraphs there. Okay, so some key things that I want to highlight is that we are looking at the movement going clockwise, so that will be super important. We're also going to assume that it has a 10-inch radius. And then let's break down this paragraph right here. So it's saying f of t, which represents the output, is the height of the dot above the horizontal diameter, measured in inches as a function of time. So that means that time is going to be our input. We're also going to assume the tire takes 3 minutes to complete 1 full revolution, and we always start at the 3 o'clock position. That's also important in trig. All of our functions assume we start at the 3 o'clock position unless otherwise stated. Okay, and then one last thing before we start filling in the table is to start with, we're going to be thinking about the tire like a clock, and we're going to stop at these key positions. So I know it's not part of our table, but up on top I'm going to kind of write down those time frames. So we're going to start at the 3 o'clock position, then we're going to go to the 12 o'clock position, the 9 o'clock, the 6 o'clock, and then we're going to go back to that 3 o'clock position and keep rotating that tire. Okay, so now we want to go ahead and fill in our table. So we're going to start with the input of time. We know that we're starting at time 0, so I'm going to put in a 0 at the 3 o'clock position. It told us earlier that it's going to take 3 minutes to complete 1 full revolution. So that means that when we start at the 3 o'clock position, when we end up at the 3 o'clock position, it's going to take 3 minutes. And so then we want to break down the time as we hit these other key markers. So we know that the 9 o'clock is halfway around the circle. So that means if it's halfway around the circle, it's going to take half of the time. So if it's 3 minutes for the full circle, that means it's going to be 1.5 minutes to go around half the circle. Then we can also go back to this 12 o'clock position and think about how long does it take to go from the 3 o'clock position to the 12 o'clock position. So that is half of the distance halfway around. So if it took 1.5 minutes to get to the 9 o'clock position, it's going to take 0.75 of a minute to get to the 12 o'clock position. Basically, that means every quarter of a circle is going to take 0.75 minutes. So then here we're going to add 0.75 minutes, which gives us to 2.25 minutes. And then we're back to the 3 o'clock position, and then we just keep going around. So it's another 0.75 minutes to get to the 12 o'clock position, another 0.75, another 0.75, and then another 0.75. So this gives us 2 full rotations on that tire. All right, now let's go ahead and talk about the height above the horizontal diameter. So I'm going to use this ruler right here to represent the horizontal line, and we're going to think about the dot in relation to that line. So you can see here that the dot is right on top of that ruler, or that horizontal diameter. So that means that it is 0 distance above the horizontal diameter. I want to bring your attention back to the fact that the radius is 10 inches. So that means that when we get to that 12 o'clock position, it is now going to be 10 units above that horizontal line, this ruler right here. Okay, when we continue rotating the circle, we go to that 9 o'clock position, and that means we are going to be 0 units above the horizontal line. Okay, we continue moving that bike tire, so now the dot is in the 6 o'clock position, and so once it's in the 6 o'clock position, we are 10 units below the horizontal diameter. So we're going to mark it at -10, meaning it's 10 units below. And then we keep rotating that tire, and we get back to that 3 o'clock position, and that dot is now right in line with that ruler or the horizontal diameter. So we're back at 0, and then we can keep thinking about rotating that circle. So that means we're 10 units here, we're back to 0, this would be -10 because we're 10 units below, and then when we get back to that 3 o'clock position, or 6 minutes into our tire rotation, we are now at 0 units or 0 inches above the horizontal diameter. All right, so now we want to explain how the dot's vertical distance above the horizontal diameter changes as the dot travels. So if we think about our dot going from the 3 o'clock to the 12 o'clock position, that means that we are increasing that height, right? So if you go back to our table, we went from 0 to 10, so that means we are increasing the height. And then now if we go from the 12 o'clock to the 9 o'clock position, our height started at 10, and then we go down to 0. So that means we are decreasing the height. And then from the 9 o'clock to the 6 o'clock position, we again are decreasing because we are going from 0 down to -10. So we are decreasing that height. And then the last one here, going from the 6 o'clock to the 3 o'clock, we started 10 units below. We are now at the 3 o'clock position going to be at 0 units. So we're right in line with that horizontal diameter. So going from -10 to 0 means that we are increasing. Okay, so all of this is going to help us build the graph here in just a couple minutes. So one of the things we also want to think about is how the change is changing, right? So we're not just thinking about, I'm just going to draw a quick little graph here. We know it's increasing, decreasing, increasing, and then we just kind of keep going through. But these are not going to be linear functions because we're following that circle. And so we want to think about how the changes in the vertical distance change. So that's what this problem is getting at. We're going to look at just one section of that tire. We're going to think about going from the 3 o'clock to the 12 o'clock position. And so we want to think about how the changes in the vertical distance change. So if we think about our function, we know it's increasing from the 3 o'clock to the 12 o'clock position, but we want to think about how does that curve happen? So how is that change happening? And so here I've got this visual. You can see I broke it up into 4 parts. So the key is that we are breaking it up into, you can think about this angle right here is broken up into 4 equal parts. And we really want to look at the change in that distance. Okay, so here I've got the visual of the vertical distance going from one dot to the next dot. And so if we look at those vertical lines, we can see that those vertical lines are getting smaller, which means that they are decreasing. And so if the changes are decreasing, so let's write this down. So if the changes are decreasing, that means it is going to be concave down. A way to remember that is decreasing has a D, and then concave down has a D. So if the changes are decreasing, that gives us a concave down shape. So that means from the 3 o'clock to the 12 o'clock position, it is going to be curving in a downward direction as we go from one spot to the next spot on our graph. So that gives us concave down. And truly we could do that for each of those 4 sections. But I think for the purpose of this class, I can just go ahead and tell you what the concavity is between each of those other sections. So between the 12 o'clock and the 9 o'clock, it is also going to be concave down. Between the 9 and the 6 o'clock position, it is going to be concave up. And then from the 6 o'clock to the 3 o'clock position, it is going to be concave up. Okay, so we want to go ahead and graph this information, but I want to talk about some of those key features that are showing up. So what we want to do is we want our input to be with time. So I'm going to list these as the time markers. So I'll talk about it in both contexts, both the clock and the input. So here at our 3 o'clock position, we were at time 0. Here at the 12 o'clock position, we were at 0.75 minutes. At the 9 o'clock position, we were at 1.5 minutes. At the 6 o'clock position, we were at 2.25 minutes. And then back at our 3 o'clock position, we were at 3 minutes. So that is the first 4 parts of our table above. And then when we think about the output, we know that the input, we started at 0 units above the horizontal diameter. At 0.75 minutes, we were 10 units above. At 1.5 minutes, we were at 0. At 2.25 minutes, we were 10 units below that horizontal diameter. And then at the 3 o'clock position, we were back at the 0. Okay, so if we go back and think about the questions that we answered above, so when we think about the increasing and decreasing that we answered right below our table, from the 0 to the 0.75, we were increasing. From 0.75 to 1.5, we were decreasing. From 1.5 to 2.25, we were decreasing. And then from 2.25 to 3, we were increasing. Okay, and then the next question, when we talked about the concavity, we only did it from the 3 o'clock to the 12 o'clock position, and here you can see that that concave down shape is showing up on our graph. And then the rest of the concavity I showed you. All right, so, and then because our tire is continuing to rotate, we could continue to create that function. So this function that we just created here is referred to as the sine function. So we write it as y equals sine. So the sine function is spelled S-I-N-E, but typically when we write it in the function, we abbreviate it S-I-N, and then our input in this case is going to be t. So our function is going to be y equals sine of t. Okay, so this is a very common trig function. So this right here is just the introduction to that. All right, so next we want to talk about some characteristics of this function. So 3 terms that we commonly will see are the period, the midline, and the amplitude. So the period is just the distance between consecutive peaks. I also like to think about the period as how long does it take to complete one cycle. So if we look at our graph right here, 2 ways to think about it. So I'll start with the formal definition. So from peak to peak, you can see we have one peak at 0.75. We have another peak here at 3.75. And so if we think about the distance between those 2 peaks, that is a difference of 3 minutes. And so that's going with that definition. It's the distance between consecutive peaks. As I said earlier, I like to think about it as how long does it take to complete one full cycle. So here we start at the 0, we're going all the way around, and then we've completed one full tire rotation or one cycle by the time we reach 3 minutes. So whichever idea works best for you, that's what I want you to use to represent the period. So that means that our period is equal to 3. All right, next let's talk about the midline. So the midline is the horizontal line midway between the max and the minimum values. So you can see on our graph here that we are 10 units above, and then we are also 10 units below. And so our midline in this case is going to be right in the middle of the 10 and the negative 10. So in this case, our midline is going to be 0. All right, and then the amplitude is the vertical distance from the midline to the peak. So again, there's two ways to kind of think about this one. So the definition here is that we are going from our midline, which we just discovered was at 0, and then our peak occurred at 10. So the distance between the 0 and the 10 is going to be 10. So that means our amplitude is 10. Oops. And so the other way to think about it that is not in that particular definition is that if we think about the max and the min, it's always going to be half of that. So you can think about we're 10 units above and then 10 units below. For a total distance of 20 units, half of that is going to be 10. So it's just another or alternative way of thinking about the amplitude. All right, so that is it for this first problem.